Any other lab reports from Thursday? We have two handouts, guys. One yellow. One yellow, one white. Okay, guys, alkene reactions. About this reaction down here. 1-methyl cyclohexene reacting with ethanol, HF. Anybody get a product for this guy, for this reaction? How about that there? How we do? Yep. Any questions about that one? Okay, let's look at carbocation rearrangements. Guys, any questions about that one? Good morning. Any questions about the previous one? Okay, guys. Let's look at carbocation rearrangements. We introduced this one last time. HBr, we might predict this to be the major product. Bromine ended up here because cation here. But actually this is the major product. How do we get this? It's a carbocation rearrangement. It involves a skeletal rearrangement. Let's look at the mechanism. First step of the mechanism is the same as before. We have HBr, we can consider it ionized. Alkene attacks H+. We believe cation on top or bottom. Cation on bottom. UH at top, cation on bottom. Nothing new. Bromine could attack here, that would give this product. That's the minor product here. What's going on? How do we get the bromine over here? Carbocation rearrangement. To get to this product, we need nothing fancy, nothing crazy. We need this cation. Because if we have this cation, bromine could add here if we get that product. How do we get this cation? We need to look at this. We want cation here. How many H's here? 1. There's an H here. You got to know where your H's are at. Okay? Cations can rearrange. To get cation over here, what happens here is the hydride will shift over, the H and the electrons. We can show the 2 electrons breaking free of this carbon and moving over. So here's the H bonded. Okay, my finger are electrons. Somebody pull my finger. Just like that, an arrow. Pull the finger over and bond it over there. Okay? This can happen. What does this arrow movement give? It gives that cation over there. Because in this structure, how many H's on this carbon? 1. Only 1. That's why it's a plus charge. If there were 2, it would not be a plus charge. How do we know there's 1 there? Because how many are here? There's only 1. We added a new one here. Still only 1 here. But how many of your H's are here? 2. That's a neutral carbon. There should be 2 there. Indeed there is. How did we end up with 2 there? Because one of these, this one moved over and there's now 2. How many H's on this carbon? None. It's a carbocation. If there was an H there, it would not be a positive charge. Okay? So you see that H is moved over. You got to keep track of your H's. Draw them in if you want. Draw them all in. That just takes time. You just have to know they're there. Okay? This is called a hydride shift because not only did the H nucleus move, but also the 2 electrons that were bonded to the other carbon. And H with 2 electrons is a minus charge. Okay? And this is called what? Hydride. Anions are ID ending. Chloride, bromide, hydride. So this would be a hydride shift. It's a type of carbocation rearrangement because the cation is said to rearrange. Or the cation is moved to a different spot. That's what this means. Now we can make this even more precise. It's called a 1-2 hydride shift. It has nothing to do with nomenclature. That's just if the H is, if you call that the 1 position, it just moves next door, which is 2. So an H moved from here to here, 1 to 2. If an H was here, and for some crazy reason it ended up moving over there, that would be called a what? 1-3 hydride shift. I don't think we're ever going to see that. Okay? But there may be some reason where you want to clarify that it's 1-2. Okay, 1-2 hydride shift. Why would it do this? Well, this is what type of cation in terms of substitution. Secondary. What do we have now? Tertiary. So we went to a lower energy intermediate. They're both intermediates. If we were to write a reaction coordinate diagram, we would have one intermediate here, and then we would go to a lower one here, because it's tertiary, it's more stable, lower energy. Carbocations are prone to rearranging. And if you can rearrange them to a more stable cation, typically you want to do that. And for us, always do that. Now, how do you get major product? Easy now, right? What do? That bromine has been watching all this. Now, bam! Electrons make bond to carbon, and that gives us major product, right? So this is just a hydride shift that gives us the major product. And we're going to say that's going to be the major pathway. And if we were shown this reaction, we would predict this as the major product. Why do you get minor product? Yeah, you may get some because it all depends on how fast the bromine can attack. how long this survives. If this rearranges instantaneously, the bromine will never attack here. But if this survives a little bit and it rearranges slow, then maybe the bromine will attack here. And you'll get more minor product. But again, we're going to predict the rearranged product as a major product. Hydride shift. Let's look at the one below. This is a hydration reaction, just acid and water, right? Okay, you should know that. Alkene, acid and water, we're going to make what? An alcohol, right? We're going to hydrate the alkene. Standard reaction is to add water across the pi bond. Might expect this to be the major product. Okay, we have acid. We're going to make cation on top or bottom? Bottom. And then if water adds here, we would get this product after we lose the H from the oxygen. And everybody has gone through that mechanism multiple times, right? Good. But I'm showing that this is the major product. How did the OH get over here? Cation rearrangement. But hold on. This carbon has 3 methyls bonded to it. This carbon only has 2 methyls. This carbon has 1 methyl bonded to it. Now the carbon has 2 methyls. Instead of a hydride shift, this looks like what might have happened. A methyl migrated over. Mechanism, same old thing. We have H plus in water. We can just show our H plus. Electrons at pi bond attacks. UH there, carbocation here. Again, if water attacked here, we would eventually get this product after we lose the H from the oxygen. What cation do we need? Everybody agree we need this cation to give that product? How can we get that? One of these methyls, they're all 3 the same. You could move any one. Here's the methyl. My hand's the methyl, and here's the bond. Somebody pull my finger. Pull it over. Yank it over. These electrons are pulled away and moved over. What does this give? What gives that? That methyl used to be attached here, but we detached it and moved it over. Now, is there a new H here? Yeah, there's a new H there, because how many there on that carbon? 2. How many there now? There's 3 there. There's 3 there now. I just don't have it drawn in anymore. Typically, I'll draw in the new H that came in from that reaction, but it's still there. The new H is still there. There you go. Anybody having trouble seeing this? Why would it want to move over? Well, this is secondary. What is this? Tertiary. We went to a more stable carbocation. Was there an H here that can move over? No, these were all methyls. What if there was an H and a methyl? Well, maybe they could both move over, but if the methyl moves over, it may not be tertiary if the methyl moves over, if there was also an H there. Typically, you only rearrange if you go to a better carbocation. Occasionally, you may see something rearranged and go from maybe secondary to secondary. You're never going to see anything rearranged and go from maybe secondary to primary. It's not going to get to a worse cation.
Why would it rearrange from secondary to secondary?
There may be some other things going on. We may see an example. Because there's other things that can influence carbocation stability other than just substitution. Maybe some bond strain is relieved, and it's two secondaries, but when you go to a better bonding. So how does this move over? Well, that's a positive charge. And what's between these two atoms? Electrons. Electrons would be attracted here, okay? Here we go, I'm bonded to you, okay? She's a carbocation. What are these electrons going to do? They're going to be sort of retracted there a little bit, okay? But the system may be like, okay, sorry, I'm going to move over and bond to her. The electrons can just move over. That's what happens here. They like it over here. There's a transition state here, which we're not showing, and often don't show transition states. So we get here. What do we want to call this? Is that a hydride shift? A methyl. What's the generic name for methyl? Alkyl shift. Now you might want to say, well, why not call it alkyl? I would say, well, that's reasonable, but alkyl is just not used. That term's not used. Just to call it an alkyl shift. We could call it 1-2 if you want to clarify, because it went from 1 to next door, as opposed to maybe a 1-5. This could have been an ethyl, methyl. Now, if you got a methyl, methyl, and an ethyl, the methyl could shift or the ethyl could shift. And so you might get more than one possible rearranged cation. We do a reaction coordinate diagram. Reaction progress. Some type of energy. We start with alkene. Let's call it A. Start with A. We go to a secondary cation. I'm going to erase this here. Secondary cation. We then go to tertiary, but that's lower in energy, yeah? Not much lower, but we'll go to tertiary. We got to finish it up. From here, what's next in the mechanism? Our oxygen nucleophile attacks cation. That gives what? It gives this protonated species here. Then we lose the proton. What can take the proton? You could use water. There's got to be some minus here. There's got to be some minus here. You could use that minus. We can also use water to take it. This takes the H. These electrons stay behind. We get that product plus what? H3O plus reformed. Acid is reformed. The H plus was the catalyst. H plus is sitting with water. At the end, the H plus is again sitting with water. Where do we want to put this here? I'll call it B. Our final product is C. Where do we want to put B at? I'll make this a little lower. Doesn't matter on your paper. Where do you want to put B compared to 3? I mean, compared to the tertiary cation. You think B is higher or lower energy than the tertiary cation? Lower? Why lower? It will be lower because the main reason I can state is there's no octet here. Here everything has an octet. Okay? We'd come down to maybe something like this. Still a positive charge. This is B. And then we come down to what? C. Where you want to put C compared to A? Lower. This has a pi bond. We now have what? Two signal bonds made. That's the new H. Bond to H, bond to OH. Two new signal bonds. That's going to be more stable than a pi bond. Here's your water, H2O. H2O. We added water to the starting material. Okay? Here we go. Boom, 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 boom. Rate determining step, yeah? From here you start falling downhill, and that's going to be pretty easy. Going from secondary to tertiary, there is a transition state, okay, where the electrons are moving over. There's a transition state there. It's a little high energy, but once it completely moves over, it settles into this well, right? So another way carbocations can rearrange is alkyl shift. Ring expansions or contractions. This is another type of carbocation rearrangement. If you take this compound here, four-membered ring, methyl, and this vinyl group. What's a vinyl group? We can get this five-membered ring with a bromine there. Now that's an addition product because if you add HBr to the formula of this, you can get that formula. But something is going on here. What you can see if you look at the ring size is the ring has expanded. That's why it's called a ring expansion. What in the world happened here? Wait, if we just reacted the alkene with HBr and did no skeletal rearrangement, we would expect what? Add HBr across the pi bond, would bromine be top or bottom? Bottom. And so that's the addition of HBr just across the pi bond without any skeletal rearrangement. You would never put bromine there. This is not the major product. In fact, I'm not even showing it. The major product is the one shown. How do we get that? Well, the start is the same. H plus, Br minus. Electrons attack here. UH there, cation here. Bromine then attacks cation, we would get this. But instead, what happens? A rearrangement. Now, I can move this methyl over. In fact, let's move it over. Just take it loose and move it over. What would that give? That'd still be a four-membered ring, right? Give that. If bromine attacked here, that would not give that product. So that's a possible product, but that's not the one shown. That product would be what? I'll call this arrow A pathway. What if we disconnect these electrons and move them over? That is, just take this and move it over. What would that do? This is B. Can you draw what that would do? Here's how I would recommend it. Everybody's using pencil, right? These are electrons. There's the atom right there. The line is electrons. 2 electrons. I'm going to say those 2 electrons, instead of bonded there, bonded there. Just do that on your paper. What did I do? Instead of there, it's now bonded there. But this carbon is now, how many bonds here? It has to be only 3 because I removed one. It can't still be 4. Okay? So that's what I would do. I would say, hey, move it over. One way you can do it is just redraw it. That H is there, but I'm not going to draw it in. And then say, hey, instead of here, I'm just going to disconnect and connect this bond there. And that's going to be the cation. And this would be a rearranged cation. This looks a little ugly, but what size ring is that now? It's now a 5-membered ring, and if we draw it more like a nice 5-membered ring, it's like this. What's on the 5-membered ring? 2 methyls next door to each other. Okay? You can put them anywhere as long as they're next door. One there, one there. And then one methyl has a positive charge. So these are the same thing. Yeah? And once we get this, how close are we to getting? Well, then the bromide, bam, it gives final product. So this was a carbocation rearrangement. This moved over, that's B. This is the B pathway, but these electrons move over. Now, if those electrons moved over also, you get the same thing because these are identical. It's just easier to do it here because it's set up to just move over on your paper or board. That's an alkyl. I mean, this carbon, basically this carbon, instead of bonding here, shifted over and is now bonded there. So you could call it an alkyl shift, but it's mainly called a ring expansion because that's what took place here. Why did it expand? This is secondary. What do we have here? Tertiary. Went to a better carbocation. But what's another reason it expanded, other than going to a more substituted carbocation? Ring strain? Yeah. I mean, the 4-member ring has 90 degrees from 9th grade geometry, right? This wants to be 109.5. What's the best size rings? 5 and 6. It went from a 4 to a 5. Better size ring. So even, for example, if this were both secondary, you could come up with a reason why we want to do this. And indeed, if you do this reaction in the lab, that's your major product. It undergoes a ring expansion via a carbocation rearrangement. The one below is not a ring expansion, but a contraction. please do that one on your own. We'll see how you do next time. Questions about this mechanism? Carbo-cation rearrangements. Roman numeral 5, ring-forming reactions. That's why we get this ring here. You take this, it's got 2 alkenes. A diene. 2 alkenes. This diene, we'll actually cover the chemistry of dienes. Here it has 3. They have some unique. That doesn't mean we can't do some stuff here. If you react this with HI, you get this product here. It's an addition product because if you take this formula and add HI, you get that formula. But it's clearly not just an addition to one of the pi bonds. How do we get this ring? Well, one step at a time. With mechanisms, I see a lot of students just want to stare at this and be frozen. How do you do that? One step at a time. We have H+. We've only done one reaction to begin with. That's alkene reacting with H+, right? So let's do that. But you got 2 alkenes, so which one do you want to react? Well, here's the one you want to react. You want to react the one to get the most stable intermediate. Just like what we say here, is it going to be left or right? Where do you want to put cation at? Left or right? Right. Well, let me ask you this. Where do you want to put cation at? Left, right, or left, right? 4 choices. What's the best choice of all 4? 1, 2, 3, or 4. Where do you want to put cation? 2? Yeah, right there. It would be tertiary. There would be primary, tertiary, secondary, primary. So I'm going to start there because that's going to be the lowest transition state of any of my possible reactions. So do that one. So H+, now hopefully you'll be rewarded by doing that as opposed to starting with that alkene. Let's see if we get rewarded. Let's one step at a time. Let's see if we can just work our way towards it. Okay? H here. Unfortunately, I know a large number of you will not be able to show this right here. Okay? Some of you I know would be, and that's great. Okay, what can we do next? I- could add here. That's obviously not that product. So something's got to happen. Maybe you've also noticed that there's no alkene there at all. So something's got to happen to this alkene. Well, let me kind of redraw this because this, we can do different conformations. If I had this in my hand, I could spin any of these bonds. Maybe I can spin them around, and let's draw this. Here's the end. I got the end, alkene, 1, 2, 3, and then cation. Alkene, 1, 2, 3, and then cations. The cation should be there. Alkene, 1, 2, 3, cation. And the coming off the cation is what? Two methyls. Okay? This looks odd, but see? Two methyls coming off the cation. Yes, that carbon has an extra H, but yeah, it's still there. Okay? So these are the same thing. Just I rotated some bonds around so they can be close together. Okay, pi bond next to a plus charge. Can a pi bond attack a positive ion? Sure. Pi bond attack a positive ion. Does it matter if it's hydrogen? No, it doesn't matter. What if the alkene attacks a carbon plus? Can it do that? Yes, it can. And this is going to be an internal reaction. Now, when this attacks, where do we want to leave cation down here? Left or right? Right. So we want to break away from the right. And if you can imagine these electrons like a windshield wiper coming up here and bonding. Pull the electrons up. What does that give? Boom, two methyls. Boom, boom, boom. All right. There's the alkene. When I move the pi bond over here, the windshield wiper over, it's right there, but I windshield wiper it over to bond there. Where's the cation at now? This was AB. That's your alkene, right? This is AB. Where's it at? It's on B. Because when the pi bond reacts, it breaks away from carbon B and goes reacts with the carbon, makes a single bond to carbon, leaving carbon B as what? A cation. It's missing a bond. Okay, are we home free now? What do we have? We now have a 6-membered ring, carbon with two methyls, and then not the adjacent carbon, but the next one has an iodine. How in the world did we get an iodine there? These electrons, bam, make a bond to the carbocation. Here's this. Two electrons in the bond there used to be a lone pair on iodine. Now the two electrons are bonded to the carbon. You have a two-electron covalent bond. The two electrons supplied from the iodide. I think that's just folded there, but here we have an alkene attacking the carbocation. So that's new, but is it really? I mean, it's an alkene attacking a cation, just like this alkene attacking it. This is what do you call it when a reaction is internal? Intramolecular. This reaction, it's one molecule that reacted internally. What do you call it when you get two different molecules reacting? Intermolecular. Two different molecules, just like an interstate goes from two different states. It's an intramolecular reaction. It's a ring-forming reaction. Because usually a ring-forming reaction, to make a ring, you got to come together. It's usually an intramolecular reaction. Once you see that mechanism, does it sort of look like, okay, that's much more straightforward than it looked at the beginning? Hopefully see it's only a wee little bit different from sort of the basics. Okay. What else was there? A little THC. Ring-forming reactions. Via alkene attacking cation within the same molecule. That's what we just did. An example of that. What about other nucleophile attacking cation within the same molecule? Well, back up here. This is an alkene attacking, but we've attacked other things. What if there was an OH over here? Like maybe an OH hanging off. Could you envision this attacking here? Just like water. So that would be an example of another type of nucleophile attacking internally. Alkene can attack, or maybe an OH can attack. Well, the OH attacking is seen in the mechanism here. This is THC. It's found in some vegetation. SC and S effects. So does this. This is called CBD. But THC is made from this. The plant makes it from this. This molecule with an acid catalyst, H+ catalyst. You can get this. Well, you got to see what's going on. What's going on? This ring is being made. If there's no ring here, 6-membered ring. How might this happen?
In the ring, why isn't there carbokinase rearrangement or alkyl rearrangement so that it goes back to the other side? So it's perhaps a tertiary, so that iodine is added there in the bottom.
Down here. Well, this is tertiary. Our original cation is tertiary. You want the tertiary to rearrange?
So whenever we get ready to add the iodine back, why doesn't it rearrange back to the other side?
Oh, you mean here? Why doesn't
Yes.
this rearrange?
Or are alkyl shifts possible?
They're always possible. How would you rearrange this though? What type of shift?
Put it where the two micrograms are.
Okay, but mechanistically, what would you do?
There's no.
There's got to be a mechanism that you show and propose and say, and then argue for. I'd have to see your mechanism. No, we can't just erase a methyl and move it over. What we did is we have electrons next door, and they became attracted to the cation and they moved over, and that's what we're showing on the board. You have to show me your mechanism. If you want to do that, please do. We can look at it. I mean, this could do it. You could do a hydride shift. Well, these H's could move a cation here, but that'd still be secondary. From there, you can move a methyl here, and you can do tertiary. But hold on, though. This was not a predictive product mechanism. This was not a predictive product reaction. Very important. The product was given. Product's given. That's it. You need to show a mechanism for giving this. There's no predicting products here. And to get that product, iodine just adds there and you're done. So that's important. Whenever you're given a product that's shown to show mechanism, you're asking, show mechanism for this. Now keep in mind, sometimes a mechanism question may show you a product that is not the major product. Maybe it's formed in 1% yield. But still there's a mechanism for forming that product. Okay, let's look down here and bring in the idea of polymerization. So do the, try the THC mechanism on your own. Should be pretty straightforward. Polymerization. If you take this guy here, what's the name of this guy? in lab this week, we'll meet downstairs and we will discuss, see if there's any questions about the alkene nomenclature, including the EZ terminology for stereoisomers. Okay? See what type of questions you have about that. Based on the questions that have been asked in class, you're a little leery about if there will be any questions there. It's up to you guys to ask questions. Okay? A number of you are coming by office hours and asking good questions. They're organized. I've seen others that come by and have done very little work. If you come by to office hours, please bring your textbook. Okay? Take this propene. You don't need to call it 1-propene because there's no such thing as 2-propene. Propene, H plus catalyst, we can get a polymer. Polymer would be shown like this with a repeating unit shown in parentheses with N being some huge number, like 100 gazillion. That's what a polymer is. The monomer initial unit just repeats many times. If this was a benzene ring here, that would be called styrene, and if you had benzene rings here, 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 it would be called polystyrene. And polystyrene, if you blow air through it, you get styrofoam. You can blow air through it and form maybe paper cups, styrofoam cups. Polymers, very important. How would this happen? H plus catalyst is all you need. The first step is just like before. This attacks H plus. Where are we going to leave cation at? Right or left? Right. Correct. So this attacks here, and we get this cation. Do I need to draw in the new H? You know it's there. Let's draw it in. Because it's actually drawn in over here. Here's the new H that begins it all. Okay? Now, choice of catalyst is important. We'll talk about it, but there's no anion here. Well, there's an anion. There's no anion that's going to react. We'll talk about that. What can react here? What reacts here? Very similar idea to above. Another alkene can react with this cation. It's not going to be intramolecular, it's going to be intermolecular. Can this alkene react here? It's going to start self-reacting. If this reacts here, where are we going to leave cation? Top or bottom? Bottom. So this swings up, attacks cation. What does that give? I'm going to draw it a little bit differently. I'm going to put that new H here. And then this here we got boom, boom, boom. Plus. I like to show what bond just formed. This bond just formed. Because if we letter this here A, B, C, isn't this making a bond to B? A, B, C. That's the original A, B, C. We call this 1, 2, 3. Based on our arrow, which carbon is bonding to B? 1 or 2? 2. Not 2. 2 is where we're leaving the cation. The electrons are 1, 2. The electrons break away from 2 and go bond to B. 1 is bonded to B. Leaving 2 is the cation. Right? Don't we say, where do you want to leave cation? Top or bottom? 1 or 2? 2 is the cation. See, this swings away and goes bonds. 1 is bonded to B, leaving 2 the cation. 1 is bonded to B. 1, 2, 3. 1 is bonded to B. And I indicated that with a little like squiggly line. That's the bond we just made. Okay. Now we got a new cation. What can attack it? Well, another alkene. Where do you want to leave cation when this attacks? Let's call it 4, 5, and 6. Which atom do you want to leave the cation on the alkene test? 5. Which atom is going to be bonded to 2? Yes, this swings up. And what do we get? H, boop, boop, boop. I'm going to do this kind of zigzag. We'll renumber it. Boop, boop, boop. A, B, C. One. That's not right, dude. 1, 2, 3. I'm trying to get good bonding because we're about out of time. I'm going to draw this up. 3. 2 was the cation. I just redrew this. 2 is the cation. Now we got boop, boop, boop. We made this bond. This is 4, 5, and 6. 4 bonded to 2. That's what we're doing right here. Leaving cation where? On 5. What can happen next? Same thing. Do it 100 gazillion times. We would need a board 100 miles long. What do we have? Let's finish up here. It's basically going to keep repeating. The H is what began. Then it repeats. CH2 carbon methyl. CH2 carbon methyl. CH2 carbon methyl. We keep on. That's what it is. We can say CH2 carbon methyl in parentheses. That just repeats if you look at it and keep growing it. Indeed, please look at it and keep growing it. This just repeats a huge number of times. That's what I got drawn here. CH2 carbon methyl, CH2 carbon methyl, CH2 carbon methyl. Just keeps on and on and on. Okay? Please look at this and we'll see what type of questions are on Friday about polymerization of alkenes. We'll meet downstairs in lab. Everybody know we're doing the